2325. All right, and so if you guys have any questions about peer tutoring or PLTL or SI, we'll be happy to answer those questions at the end of this workshop. But for now, let me go ahead and get started. Great. And then actually, just before I get started, so if you guys want to communicate with us, you can ask us any questions at any time. There's a couple options for how you do that. So you see that Yash posted a message in the chat. So if you guys want, one way to communicate is to post in the chat. All right. So to get to the chat, if you guys don't know, in the bottom right corner, there is a little purple button. So if you click on that button, the menu pops up. And if you click on the fourth icon from the right, or the first one on the left, that is the chat icon. Yeah, so then you guys are able to post messages in the chat. Now, the microphone should be enabled for you guys as well. So if you do want to speak up through your microphone, there is like a microphone icon. It's kind of close to the bottom center of your screen. So if you click on that, that will unmute your microphone, and then you'll be able to talk to us. So it's up to you whether you want to use your mic or communicate through the chat. Hopefully there won't be too many issues with like 100 people trying to talk at once. But all right, so I'll go ahead and get started now. All right, so first I'm going to talk about what is a vector, okay? So here I've kind of written down a rough definition of a vector. Okay, so a vector is something that has a magnitude and a direction associated with it. And here I've listed some examples from physics. So sort of the prototypical example of a vector would be the velocity. Okay. So velocity has two characteristics. One is its magnitude, which is just its speed. But then, of course, velocity also has a direction associated. So if you are moving at 2 meters per second east, that's going to be different from moving, well, here I have an example. So if you're moving, say, 3 meters per second east, that's going to be different from moving 3 meters per second north, okay? So the direction is important when you're talking about velocity. And so quantities that have both magnitude and direction, those are what we call vectors. Another example of a vector that I have listed here from physics is force. Okay. So you guys will be learning more about velocity and force in the two physics workshops tomorrow and Wednesday. Does anyone else, or can anyone else think of other examples of vectors aside from velocity and force? Yeah, so acceleration is another example of a vector quantity, as well as position. Now, distance is not a vector quantity, though. So distance is the magnitude of like your displacement or position. Yeah, that's good. Okay. All right, so you guys will learn a lot of different vector quantities such as velocity and force in physics. All right, so here I've mentioned that vectors, we can sort of depict or visualize them as arrows. Okay, so the length of the arrow would represent the magnitude of the vector, and then of course the direction that the vector points in would represent the direction. So looking at the two examples that I have here, so if, let's say we're talking about an object which is moving at 3 meters per second east. So if I wanted to draw a picture of that, well, okay, so east, let's say east is pointing towards the right. And here I've drawn a vector which has a length of 3, as you can see. So that would be representing the fact that its magnitude is 3 meters per second. Whereas in contrast, if you had an object and let's say the velocity was 3 meters per second north, then I might draw a vector pointing northwards. And again, I have like the length would be 3 right now, indicating that the speed or the magnitude was 3 meters per second. Okay. Now, two vectors are considered equal if they have the same magnitude and also the same direction. So, for instance, and these two examples over here, these two vectors, they have the same magnitude. So both of them have a length equal to 3. Okay. But we still consider them different vectors because they're pointing in different directions. Okay. All right, but let's say if I draw one vector like that, let's say I'll call this vector u. And then if I draw another vector over here, maybe like that, if I call this vector v. Okay. All right, so if you look at these two vectors, they are pointing in the same direction, so they're parallel to each other. And they also have the same magnitude as well, the same length. So if they have the same length and point along the same direction, then we would consider the two vectors u and v to be equal to each other, okay? All right, so at this moment, let me just kind of pause and talk a little bit about the notation for vectors. So as you can see, I'm using this notation where to denote a vector, I might assign it a letter name with a sort of arrowhead on top. So that's going to be the notation that I'll be using for vectors in this workshop. But other notations that you might see like an arrow with like a full arrowhead on it instead of like a half arrowhead like I'm going to be doing. So that's another notation for vectors. And when you're reading textbooks, you'll commonly see vectors denoted in like a bold type font to distinguish from non-vector quantities, okay? So there's no like standard convention per se on how to denote vectors, so maybe pay attention to what notation your professors might use, what notation your textbooks might use, okay? All right. You guys have any questions about anything so far? All right, you can always post a question in the chat or speak up through your mic at any time, all right? Okay, so I've kind of introduced the notion of a vector, so something with magnitude and direction. All right. So in contrast, a scalar is something that has magnitude only, so there's no sense of direction for scalars. Okay. So here I've listed some examples of scalar quantities in physics. So I have the mass as well as the temperature as two examples of scalars. So looking at temperature, for instance, we might say that the temperature outside is I don't know, maybe it's like right now, I'm not sure, maybe I'll guess 35 degrees Fahrenheit. Okay. But I wouldn't say that it's 35 degrees Fahrenheit and it's like pointing, north, right? We don't have temperature doesn't have that sense of direction that we associate with it. So you might say it's 35 degrees Fahrenheit, or maybe like if it were really cold, it could be like -10 degrees Fahrenheit or something. But you wouldn't say that's pointing in any particular direction. All right. Can you guys think of any other examples of scalar quantities? All right, yeah, so those are good. So yeah, speed is the magnitude of the velocity. Distance is magnitude of displacement. So distance and speed are both scalar quantities. That's good. Length and energy, yes. Volume and area, I think we would typically consider those to be scalars as well. All right. Yeah, I think perimeter you could also then consider as a scalar quantity then. Okay. All right, great. So as you can see, scalars, since they only have a sense of magnitude to them and no direction, we can represent scalars algebraically. As numbers, okay? So for instance, here, when we're talking about temperature, we can just say it's 35 degrees Fahrenheit, negative 10 degrees Fahrenheit. So to talk about a scalar, or to describe it, we can describe it just by using a number, okay? So what I'm going to talk about next is how can we represent vectors algebraically as well, okay? Ah. Okay. So we want to be able to do some math with vectors. And so in order to do that, it'll be useful to have a way of representing them algebraically so that we can then do things such as adding them together and whatnot, okay? All right, so how we represent a vector algebraically depends on the number of dimensions that we are working in. So I'm just going to start with the simplest case where we're going to be looking at vectors in one dimension. Okay. So if we are in one dimension, then that means that we would be constrained to a line, okay? So in some problems that you might encounter in physics, if consider a simple situation where you take an object and you just throw it straight up into the air, and then you let it fall straight down. So all of that motion is happening along a line. In that case, it would be along a vertical line. Here, I'm going to be drawing a horizontal line for illustration purposes. All right. So let's say we have some vectors lying along this line. So that's going to be one vector. And then maybe I'll draw another vector like that. Okay. All right. I'll call this vector u, and then I'll call this vector v. So if we want to describe these vectors algebraically, here's how we do that. So we choose an arbitrary direction along this line to be the positive direction. So I could choose either right, the direction of right to be positive, or left. I guess we usually choose right to be the positive direction, so I'm going to go with that, although you could certainly do left as well, and that would be perfectly acceptable as well, okay? All right, so if I choose the direction of pointing towards the right to be positive, then we could represent each vector as a number. So let's say for this vector u, its magnitude or its length is about equal to 2. So Since it's pointing in the positive direction, I might represent it as the number positive 2. Okay. So 2 representing its length being 2 units, and then positive indicating that's pointing towards the right. Whereas this vector v, let's say its length is 1, but it's pointing towards the left, which would be the negative direction. So I could represent this vector as the number -1. 1 because its length or its magnitude is 1, and then negative because it points left, which is our chosen negative direction. Okay. So vectors, if we are working in one dimension, vectors can be represented as numbers, just as how we could represent scalars as numbers as well. Okay. All right. Any questions about that?
Does the indicator arrow on top of the letter ever flip direction?
Yeah. No, typically we don't do that. So for instance, when I get to vectors in 2 dimensions, which is the next thing I'll talk about, so then there's a lot more directions your vectors could point in. I guess we don't want to adjust the arrow on top every time to account for all those different directions. So no, we typically always just have the arrow pointing towards the right when we're denoting vectors, okay? All right, but that's a good question. All right, any other questions? Yes, that is correct, yeah. All right, so let's go up a dimension. So let's talk about vectors in 2 dimensions. Okay, so this is the setting that I'm going to be working in for most of this workshop. And in physics, you're almost always working in either 1 or 2 dimensions in your problems. I would say it's quite rare that you have a problem that involves 3 dimensions in both physics 1 and physics 2. I think for those of you going into 2419, you'll encounter some more problems that involve 3 dimensions. And then if you go into 2415 as well, you'll certainly encounter problems involving 3 dimensions. All right. But let's talk about vectors in 2 dimensions. So being in 2 dimensions means that we're no longer constrained to be on just a single line, but we are constrained to be within a plane. Okay, so I drew a bunch of examples of vectors earlier. Let me draw a couple more. So for vectors in a plane, what we can do is we can choose 2 perpendicular and another word for perpendicular is orthogonal. That's the word that people will use, I think, more often, especially in mathematics, rather than perpendicular. So choose 2 perpendicular or orthogonal directions. One direction we might call the positive x direction, and then the other perpendicular direction, perpendicular, so at a right angle, that would be the positive y direction, okay? So, we usually choose the right direction to be the positive x direction, and then upwards to be the positive y direction. Although this is quite arbitrary, so in some problems in physics, you might prefer to use maybe a different set of orthogonal directions for the positive x direction and positive y. Okay. But for this workshop, I'm mostly going to be following the usual convention that right will be the positive x direction and up will be the positive y. Okay. All right. I'll also say real quickly, you don't have to choose 2 perpendicular directions. In theory, you could use two directions which are not perpendicular, but I'm not going to be doing that in this workshop. Many things get more complicated when you're not using orthogonal directions, and I don't think that's something that you'll have to worry about in physics or calculus. So I'll mention that's possible, but I won't go into it. So I would say in physics, maybe it's every once in a while, if you have a problem involving like circles, like you might use polar coordinates in the calculus-based physics courses, but it's going to be very seldom that you do so. Yeah, certainly in calculus, we have a workshop on polar coordinates, which I think is on Wednesday. Yeah, so we're going to talk about polar coordinates. You won't need to do much with vectors, though, when you talk about polar coordinates. That is correct. Okay. So once we choose a positive x and a positive y direction, then we can represent vectors as an ordered pair. So let's look at this vector here first, which I'll call u. Okay. So this vector, notice that it has an x component of 3 because it goes out to the right 3 units. And then it has a y component of positive 1 because it goes up in the positive y direction 1 unit. So I could describe this vector as the ordered pair 3, 1, okay? Whereas for this vector, which I'll call v, okay. So this vector, it goes to the right 2 units. So its x component would be positive 2. Right, but then it also goes down 2 units as well. So its y component will be negative 2, since it goes down 2 units, down being the negative y direction, okay? And then finally, for this third vector here, w, could someone tell me what the x and y components of w would be? All right, very good, okay? So yeah, the x component would be negative 3, because it goes 3 units to the left. And then the y component is positive 2, because it goes 2 units upwards. All right, good. All right, so I'm going to talk a little bit about vectors in 2 dimensions. Okay, so let's say here I've drawn a vector. I'll call it v. Okay. Okay. And so let's say we know its x component. I'll call it vx. And let's say we know its y component, which I'm going to call vy. Okay. So if I wanted to find the length or the magnitude of this vector, okay. All right, so first notation. Some people will use this absolute value notation sort of for the length or magnitude of a vector. So this is the notation that I'm going to be using in my workshop. But just so you guys are aware of some other notations for representing the length of a vector. You might see like a double bar kind of absolute value notation instead for the length of a vector. Another thing that I see sometimes is people will just drop the vector on top, or sorry, the arrow on top, and just do like the letter to represent the length or magnitude of the vector v. So those are some like alternative notations that I've seen before. And certainly there could be some other notations that other people use as well. So just so you guys are aware of that. Okay. But I'm going to be doing just sort of like a, looks like absolute value. That's what I'm going to be doing for my workshop. Okay, so if I wanted to get the magnitude of this vector v, so I can do that by using the Pythagorean theorem. So here we have a right triangle. So we know that a squared plus b squared will equal c squared. So that means c, the length of the hypotenuse, so the length of the vector v. We could compute it as being the square root of the x component squared, and then plus the y component squared. All right. So then just as a quick example, if I have the vector v, and let's say its components are -2 and 5. So let's draw a picture of this guy. So it's 2 in the x direction, and then 5 in the positive y direction. Okay. So this is what the vector v would look like. And if I wanted to find its length or its magnitude, it would just be the square root of its x component, -2 squared, and then plus the y component, which is 5 squared. So that's going to be 4 plus 25. So the length of this vector v would be the square root of 29. All right. So if we have the x and y components of a vector, we are able to compute its length or its magnitude. Okay, so I want to get to that later. Okay, so I want to sort of flip this right now though. So if we have the components, we can compute the magnitude of the vector v. So I want to sort of flip this and say if we have the magnitude of v, then can we find its x and y components? Okay. All right, so we have some guesses. So the answer is yes, if we have a little bit of extra information as well, okay? So here, let me draw a picture. So again, I have this vector v. Let's say we know its magnitude. So if, in addition to knowing the magnitude, yeah, if we know an angle, then we would also be able to find the x and y components. So in this picture, let's say if we were given this angle theta. Okay. Then we could use some trig to figure out the x and y components. All right, so as a quick refresher on trig, maybe most of you are familiar with SOHCAHTOA. Okay, so what did this acronym say? So SO says that the sine of an angle in a right triangle is the ratio of the opposite side over the hypotenuse. Right? The ka part says that the cosine of an angle in a right triangle is the ratio between the adjacent side and the hypotenuse. And then finally, the TOA part says that tangent is the opposite over the adjacent. So let's apply that to this right triangle that we have here. So if we look at sine of the angle theta, so sine is the opposite over the hypotenuse. So if the opposite is the y component, and then the length of the hypotenuse would be the magnitude of this vector v. So if we know the angle theta and we also know the magnitude, then we could solve for the y component by multiplying the magnitude to the other side. So we will get that the y component is the magnitude of v times the sine of theta. And likewise, if we look at cosine being the adjacent over the hypotenuse, you could solve for the x component as being the magnitude of v, and then times cosine of theta. Okay. All right, so if you know the magnitude and you know one of the angles, doing some trig, you'd be able to recover the x and the y components. All right, so let me do one example of this right now. Okay, so I'm going to draw a vector like this. Okay, so let's say this is the vector v. And here I'm just going to make up a number for its magnitude. Let's say that its magnitude is 7. And let's see here. Let's say that we are given this angle theta. And again, I'll just make up a number for that. Let's say this angle theta was 60 degrees. Okay. And then we want to figure out the x and the y components of this vector v. Okay. All right, so to do that, so let's look at cosine and sine of this angle theta right now. So in this picture, cosine of theta, let's see here, let's call this Vy, let's call that Vx. All right, now, cosine is the adjacent, which would be Vy, and then over the hypotenuse. So this time in this picture, cosine is Vy over the magnitude of V. Okay. Yeah, so that is something that you need to be aware of when you're doing these examples is you are going to need to pay attention to whether the x or y components should be negative or positive. But what I'll say right now is regarding the length of the vector v. So when we're talking about the length of the magnitude or length, those are always considered positive. Now in this case, here I've kind of set it up, so cosine of theta being the adjacent Vy, and then I do over the hypotenuse, which I'll represent by the length of v. So if we were to solve for Vy from this, we would get Vy is the magnitude of v times the cosine of theta. Yeah, so magnitude doesn't need to specify direction, but also just because it's talking about the length of a vector, we consider length as always positive. And I'll talk about 0 when I talk about when I get to the next part of my workshop. Let's see here. Okay, so if I plug in the numbers right now in this example, so the magnitude of V we had was 7. The angle we had was 50 degrees. So this would be 7. And then cosine of 50 degrees. Okay, so if we were to compute this right now, and I actually don't have a calculator on me, I forgot to grab one. Does anyone have a calculator on them? And if so, could you maybe calculate what 7 cosine of 50 degrees is real quickly? All right, I'll go for 4.5 then. Okay, thank you. All right, yeah, so we get an answer of 4.5. Now, do you guys maybe notice something that's a little bit off about that answer? The y component being 4.5. Yeah, correct. So in the picture, you see that the y component should be negative because it's going downwards. So when you're doing trig to get the x and y components, it's not going to take into account the sign of your component. So if you need the answer to be negative, you have to add a negative in the end in order to get the right answer. So that's something to keep in mind in these problems, is to make your answer negative in the end if your problem requires it. Yeah, and there's no need to use radians. In physics, you usually work in degrees. In mathematics, they seem to prefer radians, though. So, but it doesn't matter which one that you use. All right, great. And then just real quickly, let's wrap this up by getting the x component. Okay. So if we look at sine of theta, so in this picture, sine would be the opposite, so Vx, and then over the hypotenuse. So from that, you can solve for the x component as being the magnitude of V, then times the sine of the angle theta. So then plugging in the numbers in our problem, the magnitude was 7, and then the angle was 50 degrees. All right, and then 5.36, awesome. And in this picture, the x component, since it points towards the right, that means we should leave our answer as positive. So then that would be the answer for the x component. All right. So any questions about that? Yeah, so in this problem, I didn't specify any units, but you would include the units though, like say in a physics problem though. So V was a velocity vector, then you might have units of meters per second on each of these. All right, so being able to take a vector and resolve it into its x and y components, or being able to use its x and y components to get its magnitude and whatnot. So those are skills that you need in physics. So that's just kind of like a little bit of a taste of what you'll need to be doing in many of your physics problems. In mathematics, it's a little bit less important, although it could still be occasionally useful in some of your problems. All right. So then I just want to quickly touch on vectors in 3 dimensions. So I'm not going to spend too much time on this because I'll be focusing most of my attention in dimensions. That's where almost all of your physics problems are going to be in either 1 or 2 dimensions. So I'm not going to spend too much time in 3 dimensions. But just to give you guys some idea of how it works, you would choose 3 mutually perpendicular directions to be like a positive x, positive y, and positive z direction. And then if you have a vector in 3 dimensions, you could represent it as a ordered triplet of numbers. And so it would have an x component, a y component, and a z component as well. Okay. So in this picture, if it kind of helps, you can maybe think of the y and z axes as being within the plane of your screen. And if you maybe sort of imagine the x-axis as kind of like coming out of your screen. That's kind of what I try to depict in this drawing, if you will. Okay. And one thing I'll say is regarding the length of a vector. So if you wanted the length of a vector in 3 dimensions, you could compute the length by doing the square root of its x component squared, plus its y component squared, and then plus its z component squared. So you can get that also by using the Pythagorean theorem, although I think I don't have the time to get into that, so I'm going to go ahead and stop here for the moment. I think what I'm going to do right now, since I want to cover as much material as possible, I had an exercise prepared for you guys, but I spent a little bit longer talking about that than I thought I would. So I think I'm going to skip that exercise for now. I'm going to go on to the next section so I can continue going over some more material. So I want to talk about how to do some math with vectors now. So I'm going to start by talking about vector addition, how to add two vectors. So here, suppose that we have two vectors u and v. And here I'm just assuming that they have just an x and a y component is all. So to add the vectors together, all we do is we add their x components, and then we add their y components together, okay? And likewise, if you had a third component, you would just add their z components together to get the z component of the sum. All right. So just as a simple example, I have two vectors here, u and v. So if u is a vector 3, 1, and v is a vector negative 1, 1, then to add the two vectors together, adding 3 plus negative 1 gives you an x component of 2. And then adding the y components, 1 plus 1, gives us a y component of 2 as well. So vector addition is pretty simple. Just add the components together to get the sum. Now here it's good to see what vector addition looks like. So let me draw my vectors u and v right now. Okay, so here's u. And then v has x component of negative 1 and a y component of 1. Okay, so what I'm going to do first is I'm going to draw the vector v starting at the arrowhead of u. Okay. So starting at this point where u left off, I went out 1 in the negative x direction and then 1 in the positive y direction. So this would be the vector v with x component negative 1 and y component positive 1. Okay. So if you connect your vectors head to tail like this, then their sum is represented by this third edge of this triangle that the vectors u and v formed. Okay. So you can kind of see how it works. So u plus v has x and y components 2 and 2. So looking at this vector here that I just drew, notice that it has an x component of 2 and a y component of 2 as well. Okay. So hence, when you connect your vectors head to tail, their sum forms this third edge of a triangle between the vectors. All right, and then let's see here. Was there a question? Yes.
And am I right in saying when it never matters whether you draw the v first or the u first?
That's a good question. So maybe we can test that in this example, right? So if I were to draw v first, so let's do that over here. So v is negative 1, 1, so it would look like this. And then after drawing V, let's draw U starting from where V left off. So starting from here, I'm going to go out 3 units. Oh, whoops. So 3 units and then up 1. So then that would be my vector U. So then if I draw this vector here and complete the triangle, so notice this vector, it again has an x component of 2 and a y component of 2. So again, this would be U plus V. Okay. So if you will, what this kind of shows, the fact that you can start with U and then V, or V and then U. So that's showing us the fact that U plus V is actually the same as V plus U. And of course, that kind of makes sense because when you add these numbers together, it doesn't matter whether you do 3 plus -1 or -1 plus 3, okay? So yeah, that's a good question. You can start with either vector, and you'll get the same result because vector addition is commutative, okay? All right, so that's one way that you can visualize vector addition, as if you connect them head to tail, then their sum forms this third edge of this triangle here. Now, another way to look at vector addition, though, is rather than looking at triangles, if I draw the two vectors u and v, but let's say this time if I connect them tail to tail instead. So what I can do with this is if I form a parallelogram with those two vectors, I can also view their sum as being the diagonal of this parallelogram. Okay. So notice in this picture that the diagonal once again has an x component of +2 and then a y component of +2 as well. All right, so with vector addition, you can view it as like completing a triangle if you connect them head to tail. And you can view it as the diagonal of a parallelogram if you connect them tail to tail instead. All right. So maybe I'll just do kind of one more quick example. So if I have a vector u, which is maybe u is the vector 2, 0, and then let's say v is the vector, I'll do 3, 0. So if we just add them algebraically right now, so this would be the vector 5, 0, okay? Now, if I try to draw a picture of this, the picture doesn't look quite as nice this time, in the sense that when you look at the vectors u and v, notice that they are parallel to each other. So they're not going to form like any sort of triangle or parallelogram. Okay. But nevertheless, what you can do is if you connect them head to tail, then you can still think of their sum as being the vector, I guess, starting at where u starts and then ending at where v ends. So it's like going along u and then going along v. Okay. All right, but that's how vector addition works. So maybe if we ask the question, why is it that we define vector addition in this way? So it seems pretty natural to just add the components together in order to get the vector sum. But another reason for why we add vectors in this way is because this is how vectors will actually add in real life. Okay. So as an example, just sort of like imagining a simple scenario where, let's say that you are traveling in a plane, and let's say the engine is pushing the plane forwards or upwards in this picture at some velocity, which, I'll just call the velocity v. But then let's say in addition to the engine providing some upward velocity, let's say there's also no wind blowing on the plane. Let's say the wind is blowing on the plane with some velocity in this direction. So if you want to know what the overall velocity of the plane would be, well, it would be the vector sum of these two velocities. So the overall velocity of the plane would be in this direction and with that magnitude, okay? So that's kind of a simple example in physics, but it shows you how vectors add in this way naturally. So it makes sense that we would define vector addition the way that we did. Okay, so after talking about vector addition, I want to talk about some other vector operations. So another operation that we have with vectors is scalar multiplication. So if I have a vector with components vx and vy, and then if c is just representing any scalar or just a number then, so we can define scalar multiplication between the scalar c and the vector v, and all we do is we multiply the scalar into the components of v. So I have this example here where I have a vector v with components 2 and -4. So if I want to multiply the vector v by the scalar 2, that will give me the vector 4, -8. If I want to multiply the vector v by the scalar 1/2, so multiplying 1/2 into each component will give me the vector 1 and -2. And then we can also multiply our vector by, so we can multiply the vector by any number or any scalar. So we can also multiply by negative numbers as well. So let's say -1 times v would be the vector -2 and 4. Okay. And it's kind of good to see the visual effect of scalar multiplication. So here I've drawn the vector v. So x component is 2, and then y component is -4. So when you look at 2v with an x component of 4 and a y component of -8, so if I drew my picture well, what do you guys notice between the vector v and 2v? How are they related to each other? Yeah, okay. So they have the same direction. They are parallel to each other, but the vector 2v is twice the length of the original vector v, okay? So if you notice 2v, it's 1v plus another v to get to 2v's, okay? So when you multiply the vector by 2, it doubles its length. Likewise, when you multiply the vector by 1/2, it halves the length of our vector. And what happens when we multiply a vector by a negative number? So negative v, notice that when we multiply by a negative number, notice that that reversed its direction, okay? So v was kind of pointing down and right. So negative v points up and left instead. It points in the opposite direction of v. All right, so that's good. All right, and then let's see here. I guess I should move on. So I also want to talk about vector subtraction as well. Okay, so vector subtraction is works the same way as addition, except you're subtracting rather than adding the components. So if you have like u minus v, you can think of it as vector u plus the negative of the vector v. But all you do is you subtract the components together to get the difference. But as I did with addition and scalar multiplication, I want to sort of visualize what's happening with vector subtraction. So vector subtraction has a application which I think is worth noting. All right. So here in this picture, what I have is I have 2 points drawn right now. I'm going to label those points A and B. All right, and then I'm going to draw a vector connecting from A to B. And so common notation for this would be AB with an arrow on top. So this would be indicating that it's the arrow from point A to point B, okay? And let's say I wanted to find the x and y components of this vector AB, okay? So one way to think about this problem is the following. I'm going to take another point in the picture, just any other point. I'll call this point O. And then I'm going to draw 2 vectors, one from O to A, and then one from O to B. So this vector from O to A and then we have this vector from O to B. So notice in this picture, so vector OA connects head to tail with vector AB. So when you have vectors connected head to tail, remember that their sum is represented by the third edge of the triangle that they form. So that means that vector OA plus vector AB is equal to vector OB. So that tells us that the vector connecting from A to B, we can think of it as the difference between vector OB and minus the vector OA. Yeah, so that's kind of what I want to point out in this picture then. So if you just focus on the vectors in particular, so when your vectors are connected tail to tail, let me just call this U and V now. If you form a triangle with your vectors connected tail to tail, then this time the third edge of that triangle, rather than being their sum, now it represents their difference instead. So this would be vector V minus U in the picture, okay? So the way that I remember the order that you subtract in is I kind of think of it as the final minus the initial. So it's like the vector ends at v and starts at u, so final minus initial, okay? But this, being able to find the vector connecting two vectors tail to tail, or the vector connecting 2 points, that's somewhat common, I want to say. So being aware of how to do that by subtracting your two vectors is going to be useful in some problems, okay? Yeah, and that also works as well. That is correct. Yeah, great. I feel a little bit bad, but I think I'm going to skip my exercises and I'm going to keep talking more about vectors. I haven't managed my time too well, so it looks like I just won't have time for those exercises that I had planned, but I think that's okay. Uh, I want to talk about the dot product between two vectors next. So let's say that we have two vectors and it doesn't matter how many components there are. So here I've just labeled it with like n components altogether. But given two such vectors with n components, we define their dot product as follows. So you multiply their components together, and then you add all of those products up. So as just a simple example, if I have a vector u with components 3 and -2, and then I have another vector v with maybe components 2 and 1. So to compute their dot product, so I multiply their x components, so 3 times 2 is 6. And then multiply the y components, -2 times 1 is -2. And then I want to add those together. So in this example, the dot product between u and v would be 4, okay? Okay, so that seems pretty simple. Notice that the dot product of two vectors results in a scalar rather than another vector. So sometimes people will call the dot product the scalar product as well. So you might see that terminology occasionally. And so the reason people might call it the scalar product is because the product results in a scalar, all right? So we have this another operation on vectors, the dot product. And again, I want to take some time looking at the geometry associated with this operation. So it turns out that the dot product has a lot of geometry associated with it. One thing that I want to note right now is if I take a vector and I dot it with itself. Okay. So the dot product of a vector with itself, so that would be its first component squared, and then plus its second component squared, and so forth. Sure, yeah. So I'll try to point that out as I delve into some of the geometric properties of the dot product. Yes, So when we have a vector v dot with itself, notice that this gives us the length or the magnitude, of our vector. Okay. But it's the length squared, right? So recall that to get the length of a vector, we did the square root of its components squared. So I did it for 2, and I talked about 3 dimensions as well. So you can generalize that to any number of dimensions. So then looking at when you do a dot product with the vector in itself, aside from the square root, it's the same as its length, so it's the length squared, all right? So here we see a sort of connection between dot product and the length of a vector. And so there's other geometric notions that the dot product carries with it as well. So I'm going to get to another important geometric idea that's encoded within the dot product. But before that, I wanted to discuss some of the properties of the dot product. So I've listed some of the properties here already. The first one is one that we've already talked about. So a vector v dot with itself gives you the length of the vector squared. Here are some other properties. So here the dot product is symmetric or maybe commutative, if you will. So u dot v will be the same as v dot u. The dot product satisfies this sort of distributive rule. So u plus v dot w, you can distribute the w into the parentheses. So it's the same as u dot w, and then plus v dot w. And then likewise here you distribute the u to get u dot v, and then plus u dot w. All right, and then one more property about the dot product is how it relates with scalar multiplication. So if you have a scalar multiplying a vector, and then you dot with another vector, you can pull the scalar out to the front, and you can dot your vectors first, and then multiply that result by the scalar. Okay, so you can factor scalars out to the front, basically. So just as kind of like a quick example problem using these properties. So let's say we're given two vectors u and v. And let's say we know the magnitude of their sum. Here I'll just make up a number. Let's say the magnitude is 5. And then let's say though we know the magnitudes of u and v as well. So let's say the magnitude of u is maybe 2. And let's say the magnitude of v is 4. Okay, so if I have these three pieces of information given, then it turns out we can actually recover the dot product of the vectors u and v. So let me kind of illustrate how we can do that. So what I'm going to do is I'm going to start with the magnitude of the sum u plus v, and I'm going to consider its magnitude squared. So we know the magnitude squared would be 5 squared, which would be 25. But the reason why I want to look at the magnitude squared is because I want to involve the first property right now, where if I have the magnitude of a vector squared, I can rewrite that as the vector dot product with itself. So then this I could rewrite as the vector u plus v and dot product with itself. So I'm going to do that first. So now that I've rewritten this as a dot product, what can we do with this here? So one thing that you can do with dot products, because the dot product is distributive, because of these two properties, that means that in an expression like this, you can actually sort of FOIL it out. So we can FOIL this, and it would be u dot product with u first. And then we could do plus u dot product with v. and then you could do plus v dot product with u. And then finally plus vector v dot product with itself. So after we FOIL it out, here the vector u dot product with itself, so we know that's the magnitude of u squared. We know that u dot v and v dot u are the same things. So we end up with 2 u dot v's by adding these two together. And then likewise at the end, v dot v will give us the magnitude of v squared. All right, now we know the magnitude of u was 2, so this would be 2 squared is 4. And likewise, we know the magnitude of v is 4, so 4 squared will be 16. All right, so then here, with all the numbers plugged in, you can now solve for the dot product. So here, 4 plus 16 is 20. You can move it over, so 25 minus 20 is 5. And then, therefore, you get the dot product as being equal to 5/2. So this is just like a little example of how you can use these properties of the dot product. Yeah, so remember that for the dot product, we define it by multiplying their components and adding them up. Yeah, so that's not going to be the same as multiplying their magnitudes together. All right, so then after talking about these properties of the dot product, so I guess the main application of dot product is the fact that it gives us information about the angle between two vectors. And I think this is probably where I'm going to have to, this will be the last topic that I touch on for today. It turns out that if you have two vectors u and v, as I have here in this picture here, so I have my vectors u and v, and they are connected tail to tail, okay? So there's kind of two angles that you can associate as being between the two vectors. We have this angle that I've labeled as theta in the picture, and then there's kind of this bigger angle out here as well. So when we talk about the angle between two vectors, we always are referring to the smaller of the two possible angles between the two of them. And so it turns out that the dot product is related to the angle between the two vectors by this formula that I have written down here. And so I guess the sort of proof of how the dot product is equal to this expression involving the angle between two vectors. The proof is based off the law of cosines, which I have written over here. And it actually makes use of the properties of the dot product that I mentioned earlier. Yeah. Now we're getting close to 10:30. So I do want to go ahead and stop for the moment, since I know that the workshop is ending soon. All right, so I didn't get to all the topics that I wanted to cover, but hopefully that at least gives you a little bit of an introduction into the topic of vectors. And so you guys will be learning more about vectors in your calculus and physics. So they'll go a bit more in depth into the topics that I've mentioned. And you'll also learn a little bit more about dot products as well. So one topic that I didn't get to was the cross product between two vectors. And so cross product is an important topic and one that you will see in both your physics and your calculus courses.